Welcome back to this next video in which we are discussing finite dimensional vector spaces. Okay, so we've now seen the definition of a finite dimensional vector space, and we've proven that it is always possible to find a basis for a finite dimensional vector space. In this video, what we want to prove is really the star theorem of this video, which is that if you have two bases of a finite dimensional vector space, the number of elements within them is going to be the same. Okay, so let me write this out explicitly. So let's say that we have two bases. So let's have B1 here, which is a set of vectors, a finite set of vectors which obeys the properties of being a basis, so it spans the entire vector space and it is linearly independent, so it's V1, V2, all the way up to Vn here. Okay, so I'll colour this one in green here. So here's our first basis, and let's say we've also got a second basis here which we'll call B2, okay, which will contain a bunch of vectors as well, V1 bar, V2 bar, all the way up to Vm bar. Well, my claim is that the number of vectors in B1 and B2, if they are bases of the same vector space, has to equal the same thing. Okay, so little n needs to equal little m. Okay, so all bases of a certain vector space are going to have the same number of vectors in them. That's my claim. Okay, in order to prove this, it is necessary to first prove another theorem, and then once we've proven that theorem, this follows so easily from it. Okay, so we're going to firstly prove another theorem, basically. So put this aside for one moment, and we're going to now study something separate, but it's going to basically lead to a proof of this really simply. Okay, so the theorem then that I want to prove then is that if you have a set of vectors which is linearly independent, okay, so we'll call this capital L. So here is a set of vectors in our finite dimensional vector space which is linearly independent. Okay, so V1 all the way up to Vn. Okay, and we've got a set of vectors, and again it's a finite set of vectors, which spans the entire vector space. So V1 all the way up to Vn. So we've got these two sets of vectors. One of them has the property of linear independence. Okay, that's the one which we'll denote by capital L here. Okay, so that means that there's only one linear combination of those n vectors which will give the zero vector. Okay, oh, and I've just realised I should probably change the notation here. Let's make those bars, otherwise it looks as though they're the exact same vectors. Okay, so there's only one linear combination of these n vectors, v1, v2, all the way up to vn, which will give us the zero vector, and that's the trivial linear combination. Okay, and this second set here, capital S, v1 bar, v2 bar, all the way up to vm bar, this is a set which spans the entire vector space, so all vectors in that vector space can be written as linear combinations of the vectors here. Okay, what I want to prove then is that the order, the number of elements in this set of linearly independent vectors has to be less than or equal to the number of vectors in the set that spans the entire vector space, capital S here. Okay, so this is the theorem that I want to prove, and this then is going to allow the proof of this theorem to be extremely simple. Okay, right, so what I basically want to prove then is that little n has to be less than or equal to little m. Okay, so little n is the number of vectors in the linearly independent set here, and little m is the number of vectors in the spanning set here. Okay, right, so how am I going to prove this? Well, the way I'm going to do it is by proof by contradiction. So I'm going to assume that the opposite is true, and then what I'm going to show is that if the opposite were true, you can prove that this set of linearly independent vectors is not actually linearly independent. Okay, so if it were the other way round, if little m was absolutely smaller than little n, so little n, the number of vectors in the linearly independent set, was greater than the number of vectors in the spanning set, then I'm going to be able to prove that this set that I said was linearly independent is not actually linearly independent, and then therefore it's a contradiction, and the opposite must be true. Okay, so let's start this proof by contradiction then. Okay, so we are aiming then to show that the vectors in this linearly independent set are not linearly independent. So the first thing that we're going to do is we're going to use the fact that the vectors in this spanning set span the entire vector space to say that we can write all of the linearly independent vectors here as linear combinations of the vectors in the spanning set here. So let me put that down here. So I'll firstly put all of my vectors in the linearly independent set down here. So v1, v2, all the way down to vn. And remember, n is now, we're assuming, greater than m. Okay, that was the thing that we assume, okay, the opposite of what we want to prove, and we're hoping to arrive at a contradiction from that. Okay, so here is our little n vectors in the linearly independent set. Okay, so I'll colour this in purple here to remind us that this is the set of linearly independent vectors. Okay, right. Now, what I can do then is write all of these as linear combinations of the vectors in this set capital S. And the reason for that is that the vectors in this set capital S span the entire vector space. Okay, by initial definition I said these span the entire vector space. So these ones here in this linearly independent set are going to be writable as linear combinations of these ones here. Okay, so I'm now going to do that, and this is where the notation gets a little bit confusing, but you have to just get used to double indexes. Okay, so what I'm going to do is I'm going to notate the scalar coefficients that I'm going to put in front of all of these v bars, all of these vectors from the set S, as A, and then it's going to have two subscripts. Okay, the first subscript is going to tell me which vector I'm writing as a linear combination, so this 1 refers to the fact that this is going to be v1, and the second subscript is going to tell me which vector in the set S this coefficient is actually in front of. So let me write this out and you'll see what I'm doing. Okay, so v1 is going to be a11 times v bar 1 plus a12 v bar 2 plus all the way up to a1m v bar m. Okay, and remember, the number of vectors along here, this m, we are assuming that this is smaller than the number of vectors down here. So we're assuming that effectively we've got more of these equations, basically, than we have vectors in the equations. Okay, so I'll highlight in that m there in red. Okay, like so. Right, then I'll continue this on. So v2 here, it will be a21 v bar 1 plus a22 v bar 2. So I hope the double index isn't confusing anyone. I hope it's not too difficult. Okay, it's just, it can occasionally get a little bit confusing, but you just have to get used to double indexes like this. They're used all the time. So a2m then v bar m. Okay, so here then is the linear combination that we can express v2 as, and then we'll go all the way down to vn here, so that will now have n as the first suffix here. Okay, I'll just bring it up a bit, and then we'll have 1 here, v bar 1, plus an2, v bar 2, plus all the way up to anm, v bar m. So all of these aij's, these are all elements of our arbitrary field, capital F, over which this vector space is a vector space of. Okay, so we can always do that because this is a spanning set and this is a linearly independent set. Okay, so that's perfectly valid to do. Okay, so what was I trying to actually prove then? I was trying to prove that if m is less than n, I can prove that this set L is not actually linearly independent. Now, what does it mean to prove that it's not linearly independent? Well, it means that I need to find you a non-trivial linear combination of these n vectors, which is going to give the 0 vector. Okay, so I need to find some C1, and C2, C3, all the way up to Cn, such that this linear combination, C1, V1, plus C2, and that should be V2, I apologise, plus all the way up to Cn, Vn is equal to 0. So I'm trying to find coefficients C1, C2, all the way up to Cn, such that we have a non-trivial solution here. Okay, so it's not the case that all of them are just going to be 0. Okay, I want a non-trivial solution which will actually satisfy this relation. Okay, so I'm looking for non-trivial coefficients here that will actually give me 0. Okay, so how am I going to do this? Well, the natural thing now to do is plug in these formulae for these vectors. So to plug in for v1, this thing, to plug in for v2, this thing, and then so on, plug in for vn, this thing here. Okay, and indeed that's what we're going to do now. Okay, so I'll go over the page. Right, so if we're looking then at a linear combination of these n vectors, what I'm now going to do is plug in my formulae for the n vectors in the linearly independent set in terms of the spanning set. So C1 times A11 v bar 1 plus A12 v bar 2 plus all the way up to A1, and it's m v bar n. Okay, so this is my equation or linear combination of the bar vectors, which will give me the vector v1. Okay, then what I'll have is plus c2 times the linear combination of the bar vectors, which will give me v2. Okay, and this will be a21 times v bar 1 plus a22 times v bar 2 plus etc, all the way up until we have a2m v bar m, like so, and then you'll go on and on and on all the way down until you have plus cn times the final one, which is an1 v bar 1 plus an2 v bar 2 plus all the way up until we have anm v bar m. Okay, right, so this is what a linear combination then of my n vectors in that linearly independent set is actually going to look like. Okay, and I'm trying to find coefficients c1, c2, all the way up to cn, such that this is equal to the 0 vector. So I want all of this monstrosity to equal the 0 vector, and my variables here are c1, c2, cn. Remember, all of the other things are fixed. All of the a's are absolutely fixed. They were the coefficients which tell you how to get the L vectors, the vectors from the linearly independent vectors, the unbarred vectors in terms of the barred vectors. So they're fixed. I can change C1, C2, Cn to try and get the 0 vector here. Okay, so what I'm going to do then is apply distributivity and expand all of these. Okay, then I'm going to apply associativity to get the to change it from being a vector scalar multiplied by two scalars to being the two scalars multiplied together in the field, and then scalar multiplying the vector. Okay, so I'm going to again do two steps here. Okay, so what we'll end up with here is we'll have C1 times A11 in the field times V bar 1. Then here we'll have plus C1 times A12 again in the field times V bar 2, and then it will go on all the way up until we have plus C1 times A1m scalar multiplied by V bar n. Okay, so that's my first line there, and again I'll underline it in turquoise here. Then the second line, we're just doing the exact same things. So we're expanding this using distributivity and then applying associativity of scalar multiplication with field multiplication to change it from having the brackets around this thing scalar multiplied with this thing to having the brackets around these two things multiplied together in the field. So C2 times A21 times V bar 1 plus C2 times A22 times V bar 2 plus all the way up until we have C2 times A2m scalar multiplied by V bar n. Okay, so that's my second line, and I'll just do the final line here. So we'll then have plus dot 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 all the way down to the final line here, where we'll have Cn times an1 V bar 1 plus Cn times an2 V bar 2 plus all the way up until you have plus Cn times anm V bar m, like so. Okay, right. Now what we're going to do is we are trying to write this as a linear combination in our barred vectors. Okay, so I'm going to put together all the things which are scalar multiples of v bar 1, all the things which are scalar multiples of v bar 2, all the things which are scalar multiples of v bar m. And I'm going to again try and combine two steps together here. So because of associativity and commutativity of addition, I know that I can move everything around as I wish. Okay, so I can bring this thing next to this thing next to all of the things with v bar 1. Okay, and then what I'm going to do is factor out the v bar 1. Okay, so those are the two steps that I'm going to do together. I'm going to move everything around in addition and then factor out the vectors, and I'm going to do that for all of them. So let me start off with v bar 1. So in front of v bar 1, what you'll end up with is c1 times a1 1. So this bit here, I'll get my highlighter, so we've started with that bit. Then we'll have plus in the field c2 times a2 1. So this is an addition in the field and these are multiplication in the field. Okay, and then it will go on and on. So we've now got this thing here, you'll get all the others, and then you'll finally get down to this one here, and you'll get plus cn an1 times v bar 1. Okay, so that's collected together all of the thick coefficients of v bar 1. Okay, so that now I've just got v bar 1 scalar multiplied by one element of the field here. Okay, right, then let's do it for v bar 2, so we'll continue on. So we'll have now plus c1 a12 plus c2 a22 from here, and then we'll go on all the way until we get down to plus cn an2 times v bar 2. Okay, so that's all of these ones, so I might colour those in as well. So in green here, we've collected all of those terms into this. Okay, and then this will continue on all the way down to the nth vector here. So we'll have plus, I'll just move this up, right, okay, and then is this still visible? Yes, we've still got that in the camera. Okay, so then what we'll have is c1 a1m plus c2 a2m plus all the way along until we've got plus cn anm here. Okay, and all of that multiplied by v bar n. Okay, and colouring this in as well, we've got this one plus this one plus this one all collected together to make one element of the field, and then we're multiplying that by v bar n. Okay, so we want this entire thing to equal the 0 vector. Okay, so we remember are still looking for c1, c2s all the way up to cn, such that this equation is true, such that we get the 0 vector, and those things we want to be non-zero elements of the field. Okay, so we want a non-trivial solution. Okay, now, a way for this to be true then is if all of these coefficients that I've got are equal to 0. So if this thing is equal to 0, if this thing is equal to 0, if all of them are equal to 0, then it will be true that this side will equal the 0 vector. Now you might say, but isn't it possible that there are other solutions? Okay, isn't it possible that we could find another way that we could take a linear combination of v bar 1, v bar 2, all the way up to v bar n that would give us the 0 vector? Because remember, that set capital S, okay, going back here, that set capital S, we said it spanned the vector space, we didn't say it was linearly independent. Okay, so it's potentially possible that there is a linear combination of these n vectors which gives you the 0 vectors, in which you don't need to have 0 in front of all these coefficients. Okay, I would say yes, you're correct. Okay, we didn't insist it was linearly independent. But how on earth are you going to find that? Okay, I am just looking for a way for this to work. And a way for this to work is if this is equal to 0, this is equal to 0, and all the way down to this being equal to 0. If all of these are equal to 0, then absolutely I can say that the other side is going to equal the 0 vector. Okay, so if I can find a non-trivial solution for all of these coefficients being equal to 0, so a non-trivial solution in terms of these c1, c2s all the way up to cn, okay, such that all of these coefficients end up as being 0, then I'll be in business. I will then have a way of finding you a linear combination of my vectors of the set L, which I claimed was linearly independent, which gives you the 0 vector. Okay, so what I need to be true then, I need this thing to be equal to 0, so c1 a11 plus c2 a21 plus all the way along till we have cn an1, I need that to equal 0. Okay, then let's continue on, so this equation down here now, c1 A12 plus C2 A22 plus all the way along until we have Cn AN2, that needs to equal 0, and I think I'll just colour these in. So here is my first equation here. If that's equal to 0, and here's my second equation, I want that to be equal to 0, and then we'll go on, okay, down to the nth equation here. So we'll have C1 A1m plus C2 A2m plus all the way up until we have Cn ANm, and I want that to equal 0 as well. And I'll just repeat that argument. Okay, I'm not saying that the only solution to this great big thing, this linear combination in all of these vectors, v bar 1, v bar 2, all the way up to v bar n, equaling 0, the 0 vector, is that all of these have to equal 0. I'm saying I don't care about what all the solutions are, I just want a solution. Okay, and a solution is if all of these things are equal to 0. Okay, so if all of these equations are satisfied, then it's going to be true that the linear combination of the original vectors of the set L using these coefficients C1, C2, all the way up to Cn is actually going to give the 0 vector. So if I can find a non-trivial solution to this system of homogeneous equations, again, homogeneous just means that they're all equal to 0 on this side. Okay, then I will be in business. I will be able to prove that my supposedly linearly independent set of vectors is not linearly independent. Okay, now why is it the case that I will always be able to find a non-trivial solution to this system of homogeneous equations? Well, here's the reason. How many equations do I have here? I have m equations. Okay, we go down from equation 1, equation 2, all the way down to equation n. Now what colour did I denote n in? I denoted it in red here. Okay, so I'll colour this in red as well. How many variables do I have? Okay, well what even are the variables in this equation, in this system of equations? Well, they are the c's. The c's are the variables here. C1, C2, all the way up to Cn. Those are the variables. The a's are fixed, remember. They are just fixed elements of the field. Okay, now how many variables do I have? Well, I have n of those. Okay, so I'll colour this in purple here. So we have n variables. So this is looking hopeful, because what was the initial assumption? The initial assumption I was working on was that little n was greater than little m. Okay, so I am now saying that I have a greater number of variables than I have equations. Now, in any field, this doesn't need to be the real numbers, it doesn't need to be the rational numbers, it doesn't need to be the complex numbers, it can be one of our much more abstract fields. It is always true that if you have a system of fewer equations than you have variables, so if you have a system of equations where you have more variables than you have equations, you can always find non-trivial solutions. So if you have a system of homogeneous equations where all of the answers are 0, and you have more variables than you have equations, you can always find non-trivial solutions. Now, what do I mean by that? Well, hopefully it's obvious that one solution here is just to let C1, C2, all the way up to Cn equal 0. If you let them all equal 0, then of course this would completely be satisfied. Okay, that's the trivial solution. Okay, but the fact that we have more variables than we have equations means that there's going to be non-trivial solutions. Again, that will work in any field. Now, what I'm going to do is I'm going to have a break here, okay, and in the next video what I'll do is I'll give a little sort of brief explanation, or at least a bit of intuition as to why there is always, in any field, going to be a non-trivial solution to this system of homogeneous equations here. Okay, it's in brief because you can apply Gaussian elimination in any field, okay, and I will demonstrate Gaussian elimination just to remind you for the field of real numbers, because that's the one that everyone has most intuition for in the next video. Okay, so we'll have a break now.